Good morning all of you. Now this is the video lecture I am preparing for your reference. In today's lecture we are going to see basics of introduction to digital electronics. So if you go for digital electronics, so basically we have to consider what is the requirement for the digital system, what is basically digital signal. So if you go for in modern world of electronics, the term digital is generally associated with a computer, and this is because the term digital is derived from the way computer performs its operation by counting digits. For many years, the main application of digital electronics was only in the computer system, but today the digital electronics is used in many other applications like TV, radar, military systems, medical equipments, communication systems, industrial process control, and consumer electronics. If you go for digital systems, then we can consider it is defined as the signal which has only finite number of distinct values. So digital signals are not continuous signals, but they are discrete signals. And binary signal is a digital signal that has only two distinct values, either 0 or 1. So if you consider digital system, we define digital system as a system or a circuit which processes or works on the digital signals. The input signal to digital system is digital, and its output signal is also in terms of digital. So if you consider the basic logic gate in digital system, then we know different gates are available as AND gate, OR gate, NOT gate. These are the basic gates. Then universal gates we have as NAND and NOR. Then we can go for the special purpose gate as XOR and XNOR. Now I have questions for you here. How XOR gate can act as an inverter, that is nothing but a NOT gate, and how XOR gate can act as a transparent gate, that is the basic question. So if you go for XOR gate as an inverter, so this left side it indicates XOR gate symbol. A is the input of the XOR gate, B is the another input of the XOR gate, and Y is the output of the XOR gate. So this Y expression is nothing but A XOR with B, and this is the truth table given for the XOR gate. So A input, B input, and Y is output. So we have four different combinations for these two inputs, either 0, 0, 0, 1, 1, 0, and 1, 1. We know that XOR gate can act as high output for odd number of ones. If you observe first line 0, 0, your output is 0, and for 1, 1 output is 0, and for 0, 1 combination output is 1, and for 1, 0 combination output is also 1. Now how this XOR gate can act as an inverter means how it can act as a NOT gate. So here if any one of the input terminal of this XOR gate is connected to VCC, it can act as an inverter. Suppose third last row and fourth last row over here, if you connect this A input is permanently logic 1, that is VCC, means there is chance to change B input either to 0 or either to 1. So if there is a chance to change your B input either 0 or 1, as per your B input whatever you are applying, depending on that you will get output Y. So if B is 0, my output Y is 1. If B is 1, my output Y is 0. So this will happen when A input is permanently connected to logic 1. So that's why this XOR gate can act as an inverter when both any one of the input of the XOR gate is permanently connected to logic 1, then it can act as an inverter. Now we can see how it can act as a transparent gate. The same truth table we have, the same symbol of the XOR gate we have. Now how it can act as a transparent gate. Now basically before that we must know what is basically the meaning of the transparent gate. The transparent gate meaning is that whatever the input we have, the same you should get at the output side. If I have input as 0, I should get output as 0. If I have input as 1, I should get output as 1. That is nothing but a transparent gate. So that is nothing but the same as your D flip-flop. D flip-flop having the input as 0, output will be 0. Input will be 1, output will be 1. The same thing we have here in a transparent gate. If input is 0, output should be 0. If input is 1, output should be 1. That is nothing but the transparent gate. So this will happen if you observe the first two rows of the XOR gate. If A input is permanently connected to logic 0, then there is a chance to change your B input either to 0 or either to 1. Then depending on this B input, you will get output as Y. If B is 0, Y is 0. If B is 1, Y is 1. So this will happen when this A input is permanently connected to logic 0. Means, in other words, we can say that XOR gate can act as a transparent gate when A is 0, which is permanently connected to logic level low. Now, next we will switch to the number system. A number system defines a set of values which are used to represent a quantity. We talk about the number of people attending classes, the number of modules taken per students, and also use number to represent the grades obtained by the students in a test. The study of number systems is not just limited to computers, but we apply numbers every day, and knowing how number will work give us an insight into how computer manipulates and stores the numbers. So important definitions related to number system that all numbering systems have a few common elements that we can call as a radix or base. The number of values that a digit or one character can have is equal to the base of the system, which is also known as the radix of the system. For example, consider a decimal system. The base is 10 because every digit we have 10 distinct values. The largest value of the digit is always 1 less than the base. For example, largest digit in a decimal number system is 9. So 1 less than the base, that is 10. Then we must know the weight. Each place means position of a common number. Column number represents a different multiple of base or radix. These multiples are also called as the weights of the radix. That means number have positional importance. Then we must know the column numbers. The column numbers is the number assigned to the digits place in relation with the decimal point. So we have different number systems available as binary, octal, decimal, hexadecimal. So if you go for binary, we have the base of 2. The example is 1101.101. Then octal, we have the base of 8. The example is 367.12. Decimal number, the base will be 10. The example is 469.18. And hexadecimal number, the base is 16. The example is ABF.25C. So after this, we have to go for the basic meaning of the different types of codes. So what is basically the code is, when numbers, letters or text characters are represented by a specific group of symbols, it is said that the number, letter or word is being encoded. And the group of symbols, that is called as a code. So binary codes, we have the digital data which is represented, stored and transmitted as a group of binary bits. Such a group of binary bits, it is called as binary code. And the binary codes can be used for representing the numbers as well as alphanumeric letters. So applications of binary codes we can have in digital communication or in digital computers. So if you classify the different type of codes, we have weighted code, non-weighted code, reflective code, sequential code, alphanumeric code, as well as error detection and correction code. So if you consider the weighted code, then we can call these weighted codes or those codes which are based on the principles of positional weight. Each position of a number represents a specific weight, and several systems of codes are used to express the decimal digits from 0 to 9. These codes have the specific weight assigned to each digit represented by a group of bits. So example we can consider as binary or BCD. Then we'll go for non-weighted code. The codes in which the positional weights are not assigned are known as non-weighted code. The examples is XS3 and Greek code. Then we can go for the reflective code. So reflective code is the example that we can consider as example of XS3, 2421 and 5211. So 9's complement can be used in the reflective code. Then we can go for the sequential code. The example will be the XS3 and 8421. Then alphanumeric codes. This is the special code which is designed to represent numbers as well as alphanumeric characters. That is called as alphanumeric codes. Some of these codes are capable to representing the sum symbols and instructions as well in addition to the numbers and alphabet characters. Examples of alphanumeric codes are ASCII, that is we can call it as a American Standard Code for Information Interchange, and EBCDIC, that is Extended Binary Coded Decimal Interchange Code, and Holographic Code. So these are the examples for the alphanumeric codes. So if you consider the different codes, we can call XS3 code is a self-complementary code. That is nothing but we can call it as because in XS3 we get the 9's complement of the number by just complementing each bit. That means replacing 0 by 1 and 1 by 0. So that is nothing but the actual XS3 code, by that we can call as the self-complementary code. Then if you go for the sign magnitude of the numbers, we have to consider the examples of unsigned numbers and signed numbers. So if you consider the sign magnitude numbers, then it represents the magnitude bit and it represents the sign bit. Consider example of plus 89 and minus 89. So this 89 represents in terms of decimal number. That means the base of this number is 10. Just the difference is plus sign and minus sign here. So if you consider this 1011101, so this indicates the magnitude of number 89. So here plus indicates the sign bit is 0 and minus indicates the sign bit is 1. So this is the extension bit that indicates the sign of your number. If sign is 0, the number is positive. If sign is 1, the number is negative. Then we can consider the complements of the numbers. So if you go for the complements of the numbers, complements are used in digital computers in order to simplify the subtraction operation and for the logical manipulations. So 1's complement and 2's complement of binary numbers are important because we can use them for representation of negative numbers. The 1's complement of a number is found by inverting all the bits in that number. This is called as taking the complement. This complemented value represented the negative of the original number. Thus, 1's complement system is very easy to implement merely using inverters. So consider example of 1010. So change 1 by 0 and 0 by 1, that is the 1's complement, you will get 0101. So 2's complement we can find by 1's complement plus 1 or by direct method also. So 2's complement of 1010 is 1's complement plus 1. If you add 1, you will get 0110. And in direct method, you have to go from LSB to MSB side till you get the first one. Copy each bit as it is. So if you observe last bit is 0 and next bit is 1. So these two bits can be written as it is. Until and unless you will get first one, write all the bits, and then from this onwards, complement each bit. So next bit was 0, it can be changed to 1, and 1 can be changed to 0. So this is nothing but the example of the 2's complement method. Now next we can see the unsigned binary arithmetic, that we have to go for the addition operation, subtraction operation, multiplication operation, and division operation. So when you go for the subtraction operation, always for the subtraction operation we have to use the complement arithmetic number system. Now we can stop here. The further part we will consider in the next session. Thank you.